Yeah, good afternoon, students. So it's my pleasure to introduce this classroom discussion topic on another important application of the stack, that is converting the given infix expression to postfix expression. So now I would like to share my screen. Hope my screen is visible to you. Fine. So this is week 6 lecture 1 application of stack, that is the infix to postfix conversion. So how do we perform this infix expression to postfix conversion using the stack that we are going to discuss in this particular classroom discussion topic. So the summary of the previous CDT is that we had seen about this tower of Anai problem, so which is also another important application of the stack, where we are making use of this recursion. Recursion will implicitly use the system stack, that we have seen that. And this tower of Anai problem can be solved by making use of these three important steps. So we have three pegs, we can say it as, or towers we can say it as. So we want to move the disks, n number of disks from source tower to the destination tower by making use of an auxiliary tower. So like this we have taken here, and there are this is a source you have taken, and this is auxiliary if you take it as, then this is the destination tower you take it as. So we have n number of disks are there on this particular tower. So like this is disk 1 and this is disk 2 of different sizes, such that the larger disk will be always sit in the bottom, and the smaller disk will be on top of all the disks. Fine. So we have to move all these disks from source to the destination by making use of this auxiliary disk. So this towers of Anai problem can be solved by making use of this recursion. So recursion involves these three steps. So we have to move n minus 1 disks from the source to auxiliary. This is the first step. And remaining nth disk from the source, we have to move to the destination. That is the second step. And then move n minus 1 disks from auxiliary to whatever the n minus 1 disks we have. So we have to move that n minus 1 disks from auxiliary to the destination. So this is again when you are moving n minus 1 disks from auxiliary to the destination, this source will be used it as an auxiliary, and this auxiliary will be used it as a source. So in the recursion, implicitly we have used this system stack, and there are 2 power n minus 1 steps are involved to solve this particular problem, where n is the number of disks. Fine. So this is generalized formula to solve this particular problem. Now the today's classroom discussion topic, which is on infix to postfix conversion. This is also another important application of this stack. So this session objective is that it will develop the students' knowledge on the applications of stacks, that is infix to postfix conversion. The outcome of this session is that after completion of this session, students will be able to convert the given infix expression to postfix expression by making use of the stack. So what is an infix expression? Generally, this is the infix expression is the conventional method of representing the expression. So for example, if you're writing A plus B star C, for example, this is a given mathematical expression. So this expression is called it as infix expression. So infix means that the operator comes in between the operands. Infix means that the operator is coming in between the operands. So this is, you see that this is operand 1 and this is another operand, operand 2. So the operator is coming in between the operands. Got the point? So this is called it as infix expression. This is a conventional expression normally we will use when we are writing mathematically these expressions, arithmetic expressions. But computers will find this expression is a difficult to parse, because whenever we are evaluating this expression, so we need to convert this expression into another important notation called it as a postfix expression. So in this postfix expression, what we are going to get here is that, so in the postfix expression, we are going to get it as operator operand 1 and operand 2. Then after that, we are going to get it as an operator. Okay. So after the operands, two operands, operator is coming. For example, if you convert this given infix expression to postfix notation, so B star C will be applied first. So that is the reason. So when you convert this into postfix expression, BC star will get that. Then A plus BC star. Then we are going to get it as A BC star plus, this is what we are calling it as the postfix expression. So if you see here, it is easy for us to write the expressions using infix notation, but computers find it difficult to parse, as the computers needs a lot of information to evaluate this infix expression. So information is needed about operator precedence and associativity rules and brackets which overrides these rules. So this information has to be known to the computer. So the postfix notation, which was developed by John Lukasiewicz, who was a Polish logician, mathematician and philosopher, he developed this notation, postfix notation. His aim was to develop a parenthesis-free prefix notation known it as Polish notation. So the prefix notation is known it as a Polish notation, and a postfix notation which is known it as a better known it as a reverse Polish notation, RPN. So this is called it as a Polish notation is called it as a postfix, and a prefix, sorry, Polish notation is known it as a prefix, and reverse Polish notation is known it as a postfix notation expression. Got the point? So a postfix operation does not even follow the rules of operator precedence. So the operator which occurs first in the expression is operated first on the operands. For example, if you are given a postfix notation AB plus C star, so while evaluation, addition is performed prior to the multiplication. Thus, we see that in the postfix notation, operators are applied to the operands that are immediately left to them. So in this example, AB plus C star, plus is applied on A and B, then star is applied on the result of addition of and C operation. Fine. So we will see in the next session, we will see that how this postfix expression is evaluated. Fine. Now we will see how do we convert the given infix expression into a postfix notation. So what is this algorithm? So the algorithm follows like this. First step is that push left parenthesis onto stack and add right parenthesis at the end of queue. Scan queue from left to right and repeat step 3 to 6 for each element until the stack, each element in the queue until the stack is empty. So if an operand is encountered, while you are scanning from left to right direction, okay, so this queue is nothing but we are reading that infix expression in the form of a string. We are reading that just like a character array. We are reading that. Fine. So while you are scanning from left to right direction, we are repetitively performing these 3 to 6 steps until the stack becomes empty, so that all the elements in the given array Q will be processed. So when we are taking an element from the queue, if an operand is encountered, Then we are adding that operand to P. So P is nothing but, again, it is a resultant string, which is nothing but a postfix string. So if a left parenthesis is encountered, push it onto the stack. If an operator is encountered, then repeatedly pop from the stack and add to P each operator which has same precedence as or higher precedence than the operator encountered. Okay, so we have to go and pop up the operators from the stack, add those operators to the P until we are getting the operator which is having the same precedence as the current operator which we have read from the queue. So we are comparing with the operator precedence which is there in the stack. So push the encountered operator onto the stack. So if we encountered a right parenthesis, then what we have to do, we have to repetitively pop from the stack and add to P each operator until a left parenthesis is encountered. So we have to go on repeatedly pop from the stack and add those operators to P until a left parenthesis is encountered. Remove the left parenthesis from the stack and do not add it to P. Then you have to exit from this algorithm. So these are the 7 steps which are there in this particular algorithm. So it is very easy to follow that. Only we are storing or we are pushing the operators into the stack. We are pushing that. This is an operator.